Hello, everybody. How are you? We are back for Learning on Mondays. This is CSGLearn, C as an additional language with the Enceladus, who should be on the line. Are you?
Hi, everyone.
Yay, she is. All right, so we took a little break. We had the holiday last week, but we're back at it, and we're not programming in Python because we want to manage our own memory. That is what we want to do because it's painful and we're going to enjoy doing it. So I have already told, don't even bother to say it. I've already told her that you really don't want to manage memory, but tonight we are going to manage memory. We're going to do it boldly, like colors of blue that are sentient. Okay. And hello, what's up, Loafbone and Fafi? How are all of you as long as 715? Yeah, well, let's get into it. We have a lot of material to get through tonight. So I think I'm going to cut over to whiteboard mode. And I need the glove too because we're going to be drawing. All right. Oh, yeah. So where are we? We are, let's see, we're CaaAL. Lots of A's. C as an additional language. Topic 7. And this we're going to do structs and pointers. So structs will be like the relaxing part of the programming, and pointers will be the very not relaxing part of the programming. So it took a couple rolls to get that 8. Sorry about that, but maybe that was the die knew what Jesse had in store for her. I don't know. We're going to find out. So great. What is a struct? You have them in Python, but you might never have used them. Have you?
I don't think so.
Okay, they're kind of obscure in Python, so I'm just gonna pretend that you didn't use it. It does exist, but it's kind of weird. It's mostly for C binding anyway. It's not generally used in the language. So struct is short for structure, and it's a structure of data. So this is the beginning of, you can think of this as kind of like aggregated types. So if you have like an int and you have like a char pointer and they happen to be sort of related to each other, maybe it helps to think of them as the same thing. That's very descriptive. So let's group these. So like if we have kind of like grouped data, that's kind of what a struct is, like at a high level. So let's say, for example, that this is like I don't know, this is height, and this is, which I don't know why that'd be an int, but, and then maybe this is like a name. So this would be like, oops, a person's name and a height. All right, so we want to group these together because they're related. They're the same record of data, and we don't want to treat them separately. Like we don't want to keep a table of names and a table of heights because we want to know that when we're talking about one person, we have a height and a name. All right, well, C gives us a convenient way to do that. It's called a struct. So we can say struct, and we can define what the type is. So in this case, I'm building a person type. And it uses a brace, and that's a really sloppy brace.
Reminds me of objects.
It's very much like an object. In fact, objects directly come from structures. A object is quite, like in the C++ sense, is quite literally a structure that has methods as well. So I can think of this, let's say that we just build like a char. We're going to break all the rules of names and say that they're always 10 characters long, which is absolutely not true. There's a great post that I'll show you later about it. But and then we're going to say that, like, you know, this height here is also going to be related. So I've named these fields just sort of like using my standard like declaration syntax, except this is not actually allocating memory. This is just saying these are the parts of a person struct. Make sense?
And so, yeah, so somebody in chat actually brings up a question that I had as well, which is, can you implement methods on structs in C or no?
So the problem, I mean, first of all, C++ is implemented in C. So yes is the answer because anything you can build in C++, you could have built in C in the first place. The way they are generally built, the first thing you need something called a function pointer, which is basically pointer to a function. So if I have like a function that's like, like int, thing, and, let's say it takes no arguments, then I can build a pointer to that, and it's going to be the same type. So this is going to be like this is getting kind of screwed. Let's not get, I don't want to screw Jesse up that much. Yes, but yeah, yes is the answer. So once you have the notion of a function pointer, then you can just stick a function pointer in here, and that's exactly how a method is generally implemented. It uses a technique called the vtable in C++, but basically in C, absolutely you could do that. So we're not going to do that now. That's getting a little advanced. We're just going with the basic stuff. Okay, so I define this struct person, and then what I want to do is I want to actually like allocate one. So far, all I've really done is define, let's get our palette back here. All I've done is define what goes in it. So I haven't actually built one. So say that I'm inside like main, and I've got all my, main things, and I'm in here.
Your main things.
And I'm doing, and I'm returning an int because I'm a good person. And okay, so now in here, I'm going to use this as my own data type. So the data type for the declaration is going to be struct whatever I called it. So if I called it person, then I got to call it person here. And then this is going to be person A. So I'm going to call this variable PA. All right, not too big a jump. Basically, I've just defined this is a custom data type, and it's made up of these two things. So the compiler can turn that into a chunk of memory. It's going to be 10 of these, and it's going to be whatever the size of this thing is, depending on my platform. So this would be something like 32 bits, and this would be something like 10 times 8 bits.
Okay.
Unfortunately, and we're going to get to that in a moment, this isn't exactly true, but we start with the simple model first. All right, so does this make sense so far before I get to the real fun part?
Tentatively, yes.
Okay, so basically I've just defined kind of a convenient way. It's kind of like a class without methods, you could think of it. Okay. So then I go and I take my person, and I need to actually set up the variables. So in this case, I've got height, so pa.height, and I use this dot to refer to a part of the structure. So this is just a structure variable, and this is saying, okay, I want to talk about like this, some part of the structure variable, and then this is the part that I'm going to refer to. So yeah. I have a pa.height, and I can set it to, I don't know, 10 or something. And then I've got like a pa.name, and I'm going to need to copy something in there because it's a character array. So I'm going to have to use which function? Do we remember our C copy function?
Oh gosh, I'm sorry.
It's okay. It's been a while. It's str copy. So
thank you. Yes.
And I'm going to basically pass along that this is going to be like pa.name and what I want to put in there. So this is JS. All right, so that'll set up my structure with my two types. Now, if I try to print this thing out, C is going to be like, I don't know how to do that. Like, this is a structure. You gotta tell me. It'll be like, what? So you're going to have to unroll that yourself, right? I mean, C really only knows how to deal with these kind of like basic types. This sort of like concatenated, like this aggregated type, this is kind of up to you. But C does give you a way to refer to the parts of it, which is this dot operator. Okay, so that makes sense. Oh, they're saying that you're about half as loud. I'm sorry, I missed that. Let me crank up your volume.
Yeah, no worries.
All right, is that better, chat?
Hi, friends.
Let us know.
Can you
if
hear me all right?
Coming through.
Hopefully.
Okay, better.
I am projecting, I promise. All right.
Oh, I'm just really loud. Okay, I'll turn mine down a little bit. Maybe that'll be better. All right. Yeah, just get... Oh, and hey, what's up? I'm not going to pronounce his name because it's naughty. But anyway.
It's Snotty. Okay, sorry. Not what I expected.
TMD. I'll call him TMD.
There you go.
All right. So it's naughty in other languages. All right. So we know everything about structs, right?
Yes.
Good. Now, if I go and I clear all of this fun stuff, because that's life, then, and I want to go and I want to create a new structure. So give me something else. Let's. How about we work with planets?
Yeah, I like that.
All right. So, by the way, I'm including Pluto. So if you have issues with that,
You should.
Okay.
There's your official astronomer endorsement.
That's
you
good.
Should.
Good. We're on the same page. I was gonna say you're getting a big fat F. Okay. And I prepared a little bit of a data structure, which I thought we could probably use for like the previous CSV too. I had to post on the website, but so let's say that we want to have a name again, and we want to have the period. So how many days, Earth days, does it take for it to go around the sun?
Mm-hmm. Yep.
And I've got a handy table available that I'll just drop, and you can see Discord, right? Or you don't
yes,
have,
I can. Yeah, no, I can pull it up. Hold on.
I was gonna say,
there we go. Yep, I can pull it up.
I can also put it. I don't know if it's gonna work in Twitch, but I'll just drop it in the Learn channel here. So this will be our data set for tonight. And I went and pulled this off NASA, because NASA. Back in the space game again. All right. Whoops. Editorial there. So great. We have our little fact sheet. The link, by the way, for chat, just in case you're not in the Discord, is this. So what do we need to represent this data?
So we're going to need a string, right,
Yep.
for the name, and then int for the...
Well, except it's not an int, right?
Well, we haven't really talked about floats.
Oh, well,
so.
let's talk about floats.
Okay.
All right. The data type is float.
All right. Well,
there you go. We talked about floats.
Last time I asked
Good
about
talk.
if floats existed, there was like sort of a hand wavy like.
Oh, I'm not going to
later.
get into the bit pattern for them yet. Well, that's definitely like IEEE 754 is definitely later. But
no worries. If they exist, they exist, and then yes, we want floats.
yeah, the data. All right. So you would define this. How would you define this? Walk me through this.
What do you mean? How would I define it?
I mean, so what needs to go into this struct?
So we need, I think the two things that I just specified, right? So
yeah.
we
So
need,
give me some C.
Oh Lord, I'm not sure I feel comfortable
Oh,
enough.
that's fine. I'll walk you
Structs
through it.
yet.
You're not actually on the coding
Okay.
terminal yet, so you still get to put
Yeah,
me
there
to
we
work.
go. So
All right.
I think I need an example first.
That's
before I
totally
can start to
fine.
emulate.
So, I mean, strings are going to be what? Basic data type.
Care.
Yeah, exactly. I'm going to make a nice big assumption that all planets, so that we're going to call this the name, I guess, this record. I'm going to make an assumption that all of them are less than 20 characters. So let's allocate 20 characters because we're going to use a fixed size thing. And oh, and hey, what's up, Nathaniel? Oh, and by the way, Nathaniel, we do need to talk about Enterprise Season 4. I came around to your way of looking at things, but we'll get back. I was definitely wrong.
Oh no, you were wrong.
I was definitely
Wait, Evan,
wrong.
have you gotten to season 4? I don't know.
No,
what
we're
season
saving it for
Loaf
later.
Bonus
We're
is.
saving it for the Scotch part.
Okay, yep, all right.
Okay.
We gotta get through
I put it on.
Structs.
It's already on the list because I had a feeling that Nathaniel might come by. Okay, so that's going to be our name. Well, what else do we need in a planet?
So we just talked about orbit.
Yeah. So what do you want to call that? The float thing.
Float?
Yeah.
Like, you mean the name of the float?
Yeah. We have to give the record. Each of these like elements needs a name.
The period is generally what it's called.
So that's good. Let's call it period. I would worry about that just because it might be semantically confusing with an actual period, since we're going to
Or O, like O period.
Yeah.
Like the orbital period.
Is that okay? Good.
Yeah, that's fine.
I just want to make it because we're going to
Or
literally
orbital
use
P,
that
like whatever.
in syntax, so it might be confusing. All right, so we're going to define that as well. So now we've named the parts of the struct, and we're going to close it, and we're going to throw a line terminator on it. This terminator is a little bit weird, but it has to be there. So
Okay.
it's okay. You're going to forget. I forget all the time. It's just one of those things. It's not a function. Like normally when you're using these braces, it's kind of like in a function context or some sort of block context. No, this is actually just a multi-line statement. So you really need to have this
Okay.
terminator at the end. Okay. Now, if I want to define one of these, so I want to declare one. So again,
Yes.
I'm inside my main,
Mm-hmm.
and I defined it correctly. And the data type, again, is going to be the name of the struct. So it's struct, I have to use that word, planet, and then we have to give it the variable name. So let's just call this planet X. Okay, and if I want to refer to the parts of this struct, like for example, say I want to set up Mercury here in X, I need to do the name copy, which is going to be str copy. And I need to say this is X, and I'm using this period, which is why I didn't want to use that word, dot name. And then I do the thing that I'm copying over, which is, in this case, Mercury. So these work pretty much the same as normal variables. I just have to use this dot to refer to the right part of it, if that makes sense.
Yes. I was just copying down what you're. Yes. Okay.
And how do I set...
I mean that's familiar. Like that makes sense to me because with classes and stuff.
That's exactly where this is exactly where they got the syntax.
Yeah.
And then to set the O period, I'm going to do X dot O period, and I'm just going to set it to whatever the value is that I want. In the case of Mercury, I've got 87 points. Just round it off. 97. All right, so that makes sense, right?
Mm-hmm.
Okay, and I can't just print this thing out because it would have to know how to print out like the parts of it. Okay, going back to our RURI says C's not weird, it's just primitive. I mean, weird, I guess, has a perspective associated with it. So if you're not used to programming C, it's probably weird. You can still do oh yeah, and totally, you can definitely do anything you want with C. In fact, most things are implemented in C. Okay, so you feel good about you could set up a few planets kind of this way?
Yeah, I think so.
All right, now do you remember our operator to figure out how big a data structure is? Any data type?
Size of?
You got it. And
Okay.
that applies to structs as well. So I can do a size of, and I can say struct planet. And this will actually tell me how big this thing is in memory. And the thing that I'm going to discover when I do that is occasionally the size is not going to be what I think. So sometimes I'm going to get, say for example, I do something which is like a coordinate pair. So let's say I make a struct pair, and it's going to be int x and int y. And I'll just write them out as separate lines for clarity. How big do you think this would be? What's the size of one of these ints?
What, is it 32?
Yeah, typically. It's 32 bits.
And so 64 is what I would expect.
32 bits. So we would expect this to be 64 bits, which in bytes, because size of returns bytes, would be
8.
Yeah, 8. So we would expect to see 8. In this case, you are going to see 8.
Okay, all right. I was like, oh God, where's the twist?
Now, you remember how big this is, right?
Sorry, this being
a character.
I'm waiting to catch up with stream. Sorry.
Sorry.
Oh Lord, it's
Char is smaller than int.
So that one is 16.
That's a short
8?
you're thinking of.
No, it's 8.
Yeah.
It's 8.
Yeah.
There we go.
Yeah.
Yes.
This is 8 bits, and this is typically
Right.
16. So these, if I go and I put this next to each other, let's say we did weird. So let's make weird over here, and it's going to have a char for x and an int for y. How big do you think this should be?
So if the types are different, something weird's gonna happen.
Not always, but for reasons that are a little screwy.
I'm going to guess, because I'm guessing the answer is not what I think it is.
No,
so I'm
but
gonna
let's start with what
32.
we think it is. Well, we think that this int here is what size?
32.
This is 32. How big do we think the char is?
8.
All right, so theoretically 40, right?
Yes, but I'm guessing that's not true.
Yeah, well, why don't we find out? Let's go code.
Okay.
All right, well, let's get a size on that.
Okay. All right, so we're gonna first want to make.
These are normally defined in global scope. So I'm just gonna grab this and put it up here.
Alrighty, and then.
Oops.
Let me wait.
Fix the spacing. Yeah. Okay. Sorry.
Okay. There we go. And so then we're gonna have what? Char x int y. And then in main we can go. Let's see.
Yeah. Nice, you're labeling it.
Oopsies. The flash. All right. My window's goofed. Hold on. There we go. All right.
Okay, so there's a little warning here because this is actually
Oh,
a size
because it needs to be long.
Yeah, that's okay.
Oopsies. Okay, what?
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 That's not 40 bits.
And that's not even like, I guess that it might just like default to the larger one. So I was like, okay, is it just, I don't know.
I mean, now if we did this, is that bigger or smaller than what we just specified?
Wait, what did you just change?
I changed on line 4.
So that should be larger.
Yeah, it should be larger, right? But if I run this, it's 8 again.
Wait, but you said before it would be 64 if we had 2 ints. Are you lying?
Well, no, it's 64.
Oh, wait, these are bytes.
Yeah, bytes. These are bytes. So, no, I didn't lie. Didn't lie.
So it's just going to take whatever the largest type is and then give you that many for as many variables as you have?
All right, so if I throw another one on, right? Like if I make this a 3, right? And I execute it, I get the expected 12, right?
Right. So change that to char.
Yeah, let's make that a character.
And I think it's going to be the same.
It's still 12. Why?
Okay.
Is something wrong with the size of a character?
No. Unless you've been lying.
I have not been lying. A char is definitely 1.
Yeah.
So this is a good WTF right here. This is C. You want to manage memory directly, you got to know about memory. So this is kind of a screwy thing.
Okay.
The size may not be exactly the size that it needs due to alignment. So the way the processor works is it fetches, like, typically it's organized like in memory to fetch on a certain size boundaries. It's optimized in this case to fetch on 4-byte values. So if you give it like 4 bytes plus 1 more byte for a char, that'd be like a 5th byte. It can't read like one of those chars, like it can't store, like it's misaligned basically.
Okay.
So what C will do, what GCC will do by default is it'll just pad it out to sort of whatever the alignment is on your processor.
Okay.
So you'll see that show up in a bunch of like weird places. Like for example, if I do character, name, and I make it 4, how big should this be?
So 4 characters?
Yeah, it should be the size of 4 characters,
Yeah,
which is,
4.
yeah, 4. I mean,
4.
so it does what we think. But if I make it 3 characters, it's 3.
Okay.
This is kind of screwy, isn't it?
Yeah,
If I
this
make
is a
it
little bit
2,
confusing, honestly.
yeah, it's very confusing.
All right.
Okay, and if I make it 3 and then I throw an int in there under it, so it was 3 a moment ago.
Mm-hmm.
Now it pads it up to 8. But if I make this 4, then it's still going to stay 8. So be careful, is what I'm
That
trying
doesn't
to
make
warn you.
any sense.
Okay, no, it does make sense from a hardware perspective. It does not make
Okay.
sense from a code perspective. Like, so from this code, it looks like it should be whatever the minimum size is to capture this data. But that's not exactly what happens on the stack when, or, well, in general memory access. Like, be on guard, basically.
Okay.
So should structs not be defined closest to where they're used? I realize that's normally global scope, but sometimes, yeah, I mean, are you that is, you could. It's most of the structs that she's going to be seeing are going to be in global scope, so I figured let's just start with that. So yeah, and this is bytes. Okay, they all caught up. Greetings from Australia. What's up, Australia? Atipidian. I don't know. Yeah, project. This is about learning C. This is C as an
Is it
additional
like really?
language.
It's like 8 a.m. in Australia, isn't it?
Yeah, I know. That's
Like
crazy
12-hour
tech.
difference, I think. My aunt lives in Brisbane, so.
Brisbane, nice pronunciation there too.
Do
That's. I think
there-
the
what
Australians
if
are
we-
going to be happy about that.
people pronounce it differently?
And Rui, you're jumping ahead. Stop giving it away. That's what's coming next.
Oh, I was off. Okay, so it's because of daylight savings. My bad.
Yep.
I always forget to take that into account.
So as Rui, Ruriui, I think is probably closer, is mentioning there is a way that we can actually tell C, no, I don't want you to go screwing around with the actual memory usage and, make the alignment be all happy and good. I want you to allocate exactly what I'm telling you to allocate. And in the simple case here, which I had kind of before, where we sort of have like a 1 byte and a 4 byte, and we would think it's 5 bytes, but it's 8 bytes because it's padding it up to the data type. We can actually add in a little bit of syntactic sugar, because underneath this interpreter is actually GCC, and this is a non-standard C extension. So although it's non-standard in the sense that everybody's got it nowadays, but and this packed, so this is a little bit outside the language, and that's why it doesn't really look like it fits, with this.
Yeah, I was like, what?
Yeah,
on earth?
one of
Like-
these things is not like the other.
Yeah.
This is your first compiler directive. So this is the first time you're speaking directly to a particular type of compiler. So this is not C standard, but it is important because when we run it, what happened to the size of the struct?
It became more, I would say, like accurate.
Yes,
Right.
it basically
Less
said,
space
okay,
is
fine.
space.
I will misalign memory all you want if you specify that it's going to be packed. So this is kind of important in the case where you're like writing to disk. Like if you're serializing a structure, you might want it to be exactly a certain number of bytes for whatever it is. Maybe you don't want it to be fast for memory access. GCC by default is making it fast for memory access. So it's aligning it on the memory like kind of criteria. So it is a type of syntactic salt. There's sugar. But yeah, this is your first compiler directive. So this is not a C standard thing. All right, but it all makes sense though, right?
Mm-hmm.
And good on you, Crazy Tech, starting the journey on programming. You might want the stream that's usually in the afternoons, which would be in the middle of the night for you, which is Python from scratch. But this is the more advanced C stream for today. So if you're into C, then good luck. Okay, so language wars and chat aside, let's how do we access individual members of this? So in the example that I gave you of, why don't you set up another planet like Jupiter?
Okay, so first we need to change these.
So to declare this, and by the way, I'm going to get rid of this syntactic nonsense that we don't want right now. Oh, sorry.
Ooh, now go.
I'm messing you up. I forgot about that selection issue.
So this is the one that we had before.
Mm-hmm.
Right.
I know, 715. Just add it to the long list of features I got to implement.
He's working on it, all right?
I'm working on it. It's work in progress. Okay, so yeah, we run this and hopefully it runs, right?
Let's find out. Nope.
No, it's okay. It's just a
we
warning.
need
Yeah.
this thing.
Yeah, we need that thing.
Okay. There we go.
And yeah, by the way, just to crazy text, that .eno file is C-like, but it takes away some of the nastiness from C and C++, but still stays very tight for embedded systems. So yeah, so we run this and we're good to go. Now, how would we print out the O period? Let's say that we write a function to print this thing out. So let's call it.
You can't just call it. You can't just go like x dot o period and it's not gonna.
Well, I mean, give us a function that actually produces a record on output that shows like these different fields. Like, because what I can't do anymore is I can't say printf, magical type, and then pass along x, right? Because this is not going to work. There is no format specifier.
No, but you can give it like a float or whatever and then pass it.
You can give it. So give me a function
Okay.
called display planet.
That just returns the period?
No, that'll print out all the records, all the parts of the record.
I forgot. In C, what's the convention for functions, naming them?
Yeah, no, you're good. Oh,
like camel case?
Yeah.
Or
Yeah.
Okay, all right. Okay, so then we're given, let's see here. I can just call this. Well, no, because we called it planet, so I don't know. Do I need to specify specifically that it's a planet structure in here?
Yes.
Okay, and then.
But that's just a data type, so you also need a variable name.
We'll just call it. Sure, we'll just call it X.
Yep. Maxie's loving the camel case.
Oh Lord. Oh, brain fart.
No, I'll go piece by piece. What do you want first? The name, right?
The name, yeah.
Yes.
No, I just had a brain fart about what. Thank you.
Yeah, string.
Like sitting here, like it is string, right? And just my brain was being a weirdo. All right. Oh well, hold on. And is float, how would you do that?
F.
F?
Yeah.
Okay. Just making sure. We haven't really dealt a lot with floats. So.
Yep. I figured if we were going to get into astrophysical phenomena, we should start using some sort of decimal math.
And for, let me see, I'm trying to remember. For all functions, do you, no, we're good. This should work. And then in here, we can call display planet X. That should work, right?
Yeah, let's find out. Hey, not bad. I like it.
It worked.
Now, do you remember a little bit about the stack when I was telling you about function calls and how it would wind up the stack and unwind it? It was technical.
It's one of those things I feel a little fuzzier on,
It's
but
totally fine.
I remember you talking about like bottom up and top down. But
Yes, it is very much that. So the way it's written right now, it's actually going to copy all of the parameters to the other function. So when it's setting up the function call, it's going to copy the name, which is 20 characters, and it's going to copy the O period, which is 4 bytes on a float. Now, that's not that bad, but, when you start dealing in structs, you might have something like, like geometry land masses. And, you might start having like structures that start to get really big.
okay.
So I told you before, there is one of the first uses of pointers is to not copy all of the data on the stack. Basically says like, okay, I'm going to allow you to step outside of the stack frame for a moment and look back at the original data structure as opposed to just directly copying everything. I mean, so the copy version you just did works. And it's okay because this data structure is still pretty small, but as you can imagine, structs are going to start getting very large. So how do we use a pointer to do this?
Well, so I'm not sure where the star goes, but we would want to specify, I think,
Yes.
like, right?
That's where it goes.
And then it's not going to
Nice
copy it.
joke, R-U-R-I-U-I. I like what you did there. That's
It's like a risky profession.
some math geekery. Sorry, I got distracted.
No, that's a good one.
that was good. Love me some punnery. All right, yeah, go ahead with so that's pretty good. That'll turn it into a pointer. Now the problem is now it's actually a pointer. So I can't dereference it with dot anymore because dot directly acts, it assumes that like the structure it's operating on is right there. So
Okay.
in the case here, it's saying that like name is the first part of the record and then there's 20 bytes of that. And then O period is the next part of the record and there's 4 bytes of that. But in this case, if I'm passing it in as a pointer, how big is the pointer?
However big the memory address is.
Yes.
Or like the however big the chunk of memory that the memory address points to is. So probably
No.
64.
It's the first one you
The
said.
pew pew operator.
No, strophium, don't stop that. Don't look over there. We don't get the pew pew operator. We're gonna do it the hard way
I
first.
thought he was being sassy.
No, don't.
Okay.
He is being sassy, but don't look at that. And
All right.
don't look at what Nathaniel just wrote either.
I see nothing.
So you're banned from chat for a moment. Okay.
So we can't do what Nathaniel said? Because that makes sense.
That's what we're gonna do. I mean, he's just
all right.
giving it to you. But
I mean, that.
thank you,
does make
Nathaniel.
sense.
I'm gonna give you negative points
I'm
for giving
copying
her
off
the
Nathaniel.
answer.
Teacher caught us cheating.
Okay, so how does this work at a high level? Because we're not always going to have Nathaniel with us to tell us, the correct syntax. But what do we? Although that might be convenient, Nathaniel knows what he's doing. And hello, Cam, how are you? So yeah, at a high level, this is basically this pointer. If I'm dealing with just a regular ordinary data type, I dereference it by using the pointer again. So this says, give me the piece of, take X as a pointer and go find the memory that it refers to.
Okay.
So this is now like jumping to the actual block of memory where the concrete thing is. So this is like, I had the pointer which told me the memory address, and now this star says, jump to that part of memory, and that's the base of what I'm going to do next. Okay,
Yep.
And then after that, I'm going to put that in parentheses because it's actually really low precedence for reasons that are obscure.
Okay.
So we have to put it in parentheses to say like, no, I really want you to dereference it first. So
like order of operations.
Yeah,
almost.
it's an order of operations thing.
All right.
And now that I'm pointed at the concrete memory, not the pointer itself, I can use the dot operator.
Okay.
Like,
that makes sense.
And now I can refer to name or I can refer to O period. But if I just did it straight up, if I did this, which is kind of what I want to do when I first do C, then the way C
the
is
star's applying to the whole thing.
Yeah, that's exactly what's going to happen, which is bad voodoo, because this is not the thing. This is a pointer to the thing.
That doesn't make sense.
So it's going to try to dereference in a pointer, and you're going to get to keep both pieces. Now, a modern compiler is going to tell you, no, that's not what you want to do. but older compilers will not tell you that, and you'll still see those on embedded devices like some of the ones that are getting mentioned. But fortunately, this has been around long enough that that it'll warn you nowadays. But that's basically, does that make sense for like how we're dereferencing it first and then we're looking at the part of the record? Okay, well, it turns out there's syntactic sugar for that, which is the pew pew operator.
Okay.
And the pew pew operator means exactly what we just wrote. It means dereference first and then go and pull that part of the record. So this is just syntactic sugar that means exactly the same thing.
Pew pew operator.
Pew pew operator.
I cannot believe that is actually a real thing. Like,
well, it's not called pew pew, but
what is it actually called?
The pointer dereference operator. I forget.
It's called the pew pew.
I forget the formal name for it, but it's. Okay, Strophium says it's actually the drill down operator, but I just call it the pointer dereference operator.
I like pew pew.
Pew pew is good too. I like pew. We're gonna call it pew pew.
I like pew pew. Makes me think of lasers.
Arrow, it's not really going anywhere, 715, but I guess you could call it the arrow operator. I'm not sure what the correct terminology is.
It totally looks like an arrow though.
Christopher Aurelius, I'm sorry, this is topic 7, pointers and dynamic memory allocation is a very hard place to come in if you haven't been doing a lot of C.
Hi, new friends. But it's okay. It's confusing for me too.
But don't worry, because we only have 30 minutes more of this, and then we get to the Scotch. So, okay.
Scotch and Star Trek.
We're going to get to the Star Trek thing. So we have to get through pew pew. All right. So using the pew pew operator, how can we fix our code to deal with pointers?
So I think here, so can I just kind of go, does that work? I'm not really sure how to use this thing. So
yeah, you're really trying to use this thing. That's exactly it. Yeah, go ahead, try it.
I like pew pew. Now it's angry at pew pew.
It's kind of angry because we didn't change it when we passed it in. So we changed it on line 9. So we changed our definition to accept that it was going to be a pointer, but we didn't send it a pointer. Do I have to
specify that it's a pointer?
No, the opposite. So the opposite of the pointer operator, this is dereference, which means take the value as a memory address and look into it. But here it's the concrete thing. So we don't want the concrete thing. We want what place it is in memory. So that's like get a reference as opposed to dereference.
Yes.
And that's this operator. So this would be like the opposite direction, kind of.
No wonder my visual code was cranky at me for that line. It's like, I'm doing it right. Stop getting angry at me. It's like, no, you're really wrong there.
Yeah, modern things will warn you, but we're learning fundamentals here. So we're going to do it without the IDE. All right, so we run this, and what do we get? Hey,
it worked.
Except this time we didn't copy.
Yes. So we're saving memory.
So we used our pointer, and I'm so glad we did, because that's the second part of our lecture. All right, so structs make perfect sense, right? Aside from this really weird padding thing.
As we move into pointers, would you let me go get a slice of pizza?
You can go get a slice of pizza. That's
Yay! Okay, and that'll give a chance to answer chat questions very quickly. Okay. I'm sorry, my food arrived.
No, please, go right ahead.
All right.
Oh, Nathaniel, that's the proper name, huh? That I will mention that when she gets back. That sounds like the correct way to refer to pew pew. Just Barney wanting to sound as pretentious as possible. That may be too. Once you use it for legit drill down, it makes so much sense to call it drill down operator. Yeah, I'm fine with it, Drill Down. I like your earlier pew pew operator. What IDE is that? This is not an IDE. It's this is multiuserpad, which is something that I created for these sessions, quite literally. So I've got it on GitHub, which I don't know if I got the bot to. Oh, come on, bot. So I will fix the bot later. So fortunately, we can remember this because it's not too hard. This is all under coding with some guy. And if we go here, go to coding with some guy, and this is multi-userpad. So I've been slowly trying to totally alpha unstable. I've been creating this actually live on stream for as a learning tool, and now I'm about to start the pro mode, which is for hack sessions. So, this was initial focus was really on like building enough that we could do C on the web, or we could do Python or other languages. And now the part that I want to get to is the GoldenEye mode. I want like GoldenEye 64, like split the screen 4 ways. You have 4 separate editors and everyone's hacking, and just imagine like hack day hack session is kind of where it's going next. And by the way, that I will drop a link to in chat since I need to add it. Yeah, I made the platform though, Crazy Duck. And I do stream when I work on multi-userpad. Learning stuff I always do on Mondays. So, oh, and she has pizza and she's back. So Nathaniel mentioned while you were gone that it's called the structure dereference operator is the correct name for pew pew.
Why would we call it that when we can call it pew pew?
I'm fine with pew pew, but it might, it might be awkward in like a meeting one day. You're like, well, there's a problem on line 17 with the pew pew operator.
I mean, is that not like is that? Just
I would love it if you did that at work, but I mean, different people, different styles, different companies. I mean, maybe if you're in like doing a defense contract, you don't want to call it the pew pew operator. I mean, it might have a different connotation.
I'm the only person on my contract who codes, so I'm pretty sure I could probably call it like the, Martian operator, and they'd just be like, wow, okay. So.
Okay, so you write exploits. Wow, they really started a movement. Nice job, Strophium. I like what you did. So.
You literally made it up. That's what I thought. Okay.
Okay, the ISO standard, Nathaniel's pulling up the standard and seems to say it's referred to just as the dash greater than operator.
So Strophium.
Yeah, that's
how much.
I'm not getting into that.
How much do you dare me? What do I get? And I will I wish I could record it, but I obviously can't record work meetings. I will totally say that in a work meeting because, like I said, I'm the only person who codes.
Maybe
on this contract.
Accidentally leave something open on Discord so we can hear it.
Nobody would know. No one would. I will say the spaceship operator, and they will be like, "Oh, okay, yeah, clearly, I see that."
All right. Well, listen, fun time is over because we're into pointers, and I'm putting the glove on because this is.
I have pizza.
You got pizza. I hope that brings you to a happy place.
Pizza always brings me to a happy place.
I'm gonna come back to multi-userpad, and I'm gonna switch back to whiteboard mode. All right. So we did a lot.
Wait, really quick. I'm so sorry. Yep. Is this spaceship operator a real thing?
Yeah, I'm not getting into it.
Okay. I can't tell who's joking with me and who's being serious.
Strophium brought it up. I will let Strophium talk about it.
Right.
But I think you're going to get confused enough with part 2, which is really pointers. Oh. Okay. And just because this is such a big topic, I'm switching colors because what am I thinking?
Twitter has told me to be afraid of these things.
Twitter is not wrong. So that's all I'm going to say about that.
I need something stronger than pizza.
Okay. Pointers at their core are very simple. Okay, it's just an address of memory.
Mm-hmm.
Now that's really important to memorize because they're going to get scary, they're going to get confusing, but literally at the end of the day, it's just an address of memory. So just channel that and ohm with it and go an address of memory ohm. It's just that is all a pointer is. So do not be afraid of them. Just realize that they will get you into trouble very often. And that's why we love languages like Python. So
yes, exactly.
Generally we don't have to use them. But at the end of the day, it's just an address of memory. So if I have 8 bits of memory, So if I'm on an 8-bit chip, like back in the day, or if I'm programming the Nintendo, like we're going to be doing a little bit later, then maximum number of memory locations I can have is 2 to the 8th, which is 256. I don't want to put you on the spot while you're eating pizza. So I can view memory as top down, bottom up. It depends what kind of place I am. But if we look at it, these is memory location 0, 1, 2, 3, 4, 5, all this stuff up to memory location 256.
Yep.
Okay. That's it. So that's all I'm going to get. Now, if I've got 256 different memory locations and I want to refer to memory location 5, I just call it location 5. A pointer to that is just location 5. So if I create a pointer, now if I have memory and it's organized as 8-bit blocks, so let's just pretend that...
Really quick though, so if we had something stored, let's say like an integer, well, an integer wouldn't make sense here. Let's say we had, let's say we had just something, let's call it X. I'm not going to specify what it is, stored at memory location 5. The pointer for memory location 5 is just memory location 5.
Yes.
Same as the pointer for X is memory location 5.
Yes.
Right? Okay.
Ish, I think. I actually put the letter X in here. So that might not be exactly what you mean. But like, let's say that like I had a character.
Like the pointer to the item that we've stored there is the memory location.
Okay. I'm just going to write that out so that we all don't get confused. Let's say that there's character X and it's assigned to the letter A. And that's, I don't see how that's not confusing. So let's not use characters at all. Let's just use numbers that are 8 bits wide. So we're going to use the new style types. Okay, so this is an 8. Now forget the fact that this is actually a char, but this is just an unsigned integer that's, well, actually it's really an unsigned char. So I guess int 8 would be a char. So if I have a variable there and it's called X and I assign it the value, well, let's pick a different number. Let's assign it the value 42. So if I print out X,
you get 42.
And if I can write correctly, then, and I remember this thing, and then I say this is X, then I'm going to see the number 42 show up when this thing prints out, right?
Right.
Cool. All right. Where is this in memory? I mean, this is a variable, so it's stored somewhere in memory.
Yeah, memory location, what we're calling memory location 5.
Okay, so in this case, we said the compiler assigned this to memory location 5. It's a little bit more complicated than that. There's something called ELF, and there's dynamic loading, but let's assume...
Like Santa's elves?
Yes.
All right.
We're going to get...
Just making sure I heard you right.
Yes. You definitely heard me right. We'll get into elves. There are elves hiding in this computer. All right. So...
And that other guy was saying C wasn't weird. All right.
So
spaceship operators and elves.
Okay. No, elf. Yeah, you were going to get to elf is the literal term for it, actually. But we'll get to the elf tools a little bit later. But so let's say that the compiler assigned definite static location 5. This is an old school compiler, and it literally assigns all of memory. And it chose location 5 for variable X.
Okay.
All right. Now, it knows that this is aligned properly. I'm ignoring alignment stuff, which we kind of covered briefly when we talked about structs. So how do I find out in C where this thing is stored?
The pointer?
Yeah. I would just say, give me the reference to X. This is 5. Right?
Yes.
So... If I say like this, if I use this ampersand, that's saying I don't want the variable itself, which has 42 in it. I want the location in memory of where it is. And this says, tell me where it is in memory. And it's going to say, oh, you mean this thing. You mean 5. I'm assuming you're going to do some pointer arithmetic, but compilers didn't do that till later.
So ampersand X returns a pointer.
Yeah, I mean, what is a pointer?
The memory
An
location, right?
address of memory. You have to say this
Mm-hmm.
like 1,000 times. So it's just an address of memory. So the address of memory of X is what?
5.
Yeah, and I think that this was originally called the address of operator. So, well, in the case of 5, Big Mama, I chose the number 5 intentionally so that we could avoid the hexadecimal. But yes, this would be, if you wrote 5 from decimal in hexadecimal, it would be 0x5. And if you wrote it in octal, it would be still 5. Because fortunately 5 is less than the size of those number bases. Now, if you did it in binary, you'd actually have to do a little bit of arithmetic. But we're not worried about different number representations. We got into that in like the first stream. So
Okay. Yeah.
we're not worried about this. We're not worried about this. It's just we're used to dealing in decimal numbers, so we're going to deal in decimal numbers. So we want the thing that's in memory address 5. Now, that is how I get a reference to it. So this is a C way of saying, look, compiler, tell me where you're going to put this in memory, and that's important.
Okay.
So then in order to store it and say, I want to refer to this thing as a location, like let's assign the variable Y, I can say this is going to get the address of, and I read the ampersand as address, because it's the address in memory.
Mm-hmm.
Give me the address of X. And that's going to say, well, in this case, it's going to evaluate to 5. Now, if I actually knew the memory layout of my computer, I could literally say char Y is 5. And this would be interpreted as a memory address. That would give you whatever happens to be in memory location 5. Don't try that. This is the kind of thing that wins the obfuscated C contest. So we're not going to do that. But
Okay.
it's also pretty much illegal these days, because nowadays that would be a segmentation fault, because you are reading past the part of memory which is related to you. 5 might be there or it might not, depending on where it gets loaded. Okay, great. So pointer.
You mean like something might not be there, or what do you mean it might be there, it might not
well,
be there? Like, the memory is definitely there.
No,
right?
it's there, but it might not be yours, right? Because if I have like a bunch of programs running on this computer, because nowadays we have multi-processor, multi-tasking operating systems with multiple processors and stuff like that. Your program might be here. Like this might be like the chunk of memory that's like Jesse land. Okay,
Right.
but over here might be the chunk of memory that's assigned to like some system daemon or something, So if I just refer to an address, like who knows who has 5, right? This disk is probably owned by a
Right, so
bit.
we're talking about like permissions, right?
Yeah, that's exact. These are
Okay.
all called segments, right? These are all segments. So in our modern memory model, we say that memory is segmented. So like you get this chunk, Jesse gets this chunk, system gets this chunk, whatever happens to be
Yeah.
running on the system at the time. Okay,
Yep.
so we don't typically write out the exact address anymore. We just say to the compiler, you tell me what the address is of this variable.
That makes sense.
Okay.
Also, just because there are so many addresses at this point that I imagine that becomes unwieldy as well.
Well, again, it depends on the kind of processor you're on. Like if you're dealing on like an NES, then you are going to refer to memory directly. Like
Fair enough.
like we'll be doing later on, because there's
Yeah,
something
you just
called,
mentioned like modern machines. So it's more
most modern machines are position independent, so you don't know where you're going to land in memory until execution time. So but anyway, that's getting into ELF. I don't want to get into ELF. It's an advanced topic. So
no elves for me.
okay. Moral of the story, like you're doing a bad thing, and that's actually what'll happen when you like. This is where you start going wrong with pointers. Like for example, say that you said that in our earlier example of struct planet. Let's say that we had a struct planet which was a pointer to a planet, and we just refer to it as X, and I say that X is going to be referring to the Mercury planet. Let's say I set up a variable called Mercury. Then this is fine, right? This is all valid. But if I go and I say like, X.name, Well, in my structure,
That doesn't make sense.
Yeah, I mean that's
right, because
this is an address.
is a memory address.
Yeah, so if I
it's
jump,
not the actual object.
this is really an offset, right? This ends up being like how many bytes from the start of this record is it, and that's what the struct is defining. So I got to be really careful here, right? So this whole offset thing, if I try to do an offset from a pointer, I'm going to get another data type which is not related to the data. So, and then C is just going to keep on trying to go if it can, right? As long as you don't get a segment violation. So like I said, you're lucky if it crashes. Okay, so that's why we have to start being really careful about pointers. Now, one last little bit, what if I have like, now in the example that I had like, say this was memory location 5 and I had stored 42 in here, and then I had another variable which was X, and well, actually, I think we called this X. And then I had another variable Y, and I'm just going to define Y as, actually we were calling this an int 8t, and I'm going to make this a pointer, and I'm going to say Y is going to point to a reference of X. So what am I storing in Y? Let's say this landed in memory location 12.
You are storing the memory location of X.
Yes, where is it?
In Y. 5.
Yeah. So what value's in here? 5. Because a pointer is what?
Memory address.
Yes, it's an address in memory. Okay, we just have to say that a million times if we're not going to get screwed up with pointers. All right. What if I create a new thing which I call Z, and I have it point to Y?
Z is 12.
Yeah, if Z lands over here, because it's got to stay, actually this is already illegal because this is a segment violation, but let's, you see, it's that easy. All right, so Z is going to end up with the number 12 in it. So this is a pointer to a memory address. And that's typically shown like this, which is pointer to pointer, but I could actually just treat it as a single pointer. And this is where pointer math starts to get a little bit hard.
Okay.
All right, now you've intuitively been doing this with strings. So when you had something like name and you said like, this is going to be like, and we use this syntax and we say like it's Mercury. This is valid. It's going to allocate enough room to store this, plus it's going to have that invisible null byte that we talked about before, and it's going to make this that size. Okay, now if I have like, a pointer to it, like say I have X and it points to the location of, I want to say name, except name itself is already that. But where would be the first part of memory of name? What would be the first part of that array? It'd be name sub 0, right?
Yeah.
And I could take a reference to that. So this is valid.
Yes, that makes sense.
Okay. There's a shorthand to that, which this you can just sort of refer to using pointer notation. It already is a pointer in a sense, because this is an array. So this, you can actually just do the assignment as char x is name. And this will work. It might throw a warning that this is not the same type as this, but it'll work. All right. So does all that make sense?
So I think, yes, all of it has seemed really, really intuitive until the very last thing you said, where you just kind of said, well, you don't need to have this notation. You can just kind of give and then you lost me for a sec.
I apologize. That's syntactic sugar. So when I did something like name and I said that, let's say that this thing is like 10 big, and I put in here like Jesse. Okay, this is going to be Jesse is 5 characters. This is 5. And I always have that invisible null terminator at the end of the string. So this is really going to be 6 characters wide. That's smaller than 10, so we're okay. The compiler's not going to throw anything about that. So we have a few extra blocks of memory afterwards that we're not using, but we could use it later. All right, that part you're good with.
Okay, yes.
Now, what's the first character of this?
J.
Yeah. I mean, and how do I refer to it with this variable?
Name indexed 0.
Yeah. Okay. Now, where is that in memory?
Well, wherever. I mean, we could point to it,
Right.
or we could use the
How do I
the
find
ampersand.
out? How do I? Yeah, I use the ampersand, which says,
Yeah.
"Give me a reference to this in memory." Like tell me the address, and I can assign that to another variable.
Yeah.
Like if I have a pointer to the name, like X. So X is now pointing to that, right?
Mm-hmm.
Well, it turns out that actually this is typically implemented as a pointer itself, but
What is typically?
name.
I might just be a little bit behind on this.
No, that's okay. This name in the character declaration, which refers, name itself is not
Right, that makes sense. It would be a pointer, though, right? Because that's when you're declaring a variable, you're kind of you're allocating the memory.
Yeah, it's not
So it makes sense it
actually.
would be kind
It's
of
like a pointer that's set to the start of where that chunk of memory is. So I
Okay.
can use this type of syntax, which actually works with pointers as well. So, and that's pretty much what you're doing here. It's syntactic salt, as Nathaniel is. It's not syntactic sugar. It's just painful. But name by itself is really just an address in memory. It's really the address of the first element.
Gotcha.
So I don't need the ampersand if I don't dereference it. So in this case, I dereference it. I get the J, but I want the address of where J is using this ampersand. Then that's going to be, that'll work. But otherwise, I could actually just drop all that and just say char pointer X is.
But we would have to dereference it explicitly if we wanted, say, the memory or the pointer of like S, the first S.
Yep.
Right?
Yep.
Yeah. Okay. So
Or-
we couldn't use the syntactic salt or whatever because
Well, no, I could, because where is that S? What location is that relative to the start?
+2.
Yeah, and I can actually do exactly that. I can say X plus 2. Now, this is a
Okay.
little weird because you've probably never done that.
No.
Um,
All right.
that is, so basically I'm taking, if I assign this to the first address of the array, which is kind of like the memory location here, I can say 2 locations past that, assuming that they're all 8 bits wide, is going to be 2 bytes past that is going to be where the S is. So
Right. So I guess my point was, let's pretend that you aren't. Let's say that you're not doing that char pointer X line, right? And let's say that instead you wanted just char X to be the memory location of S without that first declaration. Then you would have to use the ampersand.
I think
Because
so.
you would not be able to use that shorthand of saying char X star, like you can't say char star X equals name indexed in any way. You would first have to create that pointer, right?
I wanna actually walk through this like with real code. Like
Okay.
let's try it. So if I do like char name 10, this is the example that I was writing, and this thing is Jesse.
Yeah.
All right, so my normal way of printing this out, I can just say like, okay, do this and, do name, right? So this should work, right? Okay, so I execute this, it shows Jesse. Now, if
Yep.
I do name location 0, what do I expect to see?
J.
Not quite. This is no longer a string, it's now a character. Okay, so I change the specifier to character and we're good. It shows up as a
Yep.
J. All right, if I get the S that you were referring to before and I change the subscript to 2 and I run that, we see the S, right? But the S can also be gotten a different way. So in the earlier example, I was telling you could do this, right?
Yes.
Okay, so if
And
I
I do understand why we could do like X plus 2 and whatnot. My question was, if we don't have this line, we cannot say like Y. I don't know.
No, well, that's not a memory location.
Exactly. That was just my point, is that like you couldn't do this You couldn't have that
Wait, but
like
you
that
can
pointer.
do this.
Yes, exactly. That was my point, was that if you're going to reference an explicit letter without having first line 16, you have to use the ampersand to have that like explicit reference, right?
You do to get the memory location. The ampersand is about getting the memory location, but you don't actually have to have it, because what I could do is I could write this like this, and I could say +2.
Yeah, and that's totally fine. It was about the indexing.
Oh, okay. Okay, gotcha. Yeah.
So,
yeah. The indexing like actually gives you the concrete like memory location of that S, but it's not the memory location, it's the thing that's at that memory location, right? So you want the memory location, you have to use the ampersand. But we have a little bit of syntactic salt in that referring to name with nothing just inherently refers to a pointer to the first location.
The first location, exactly. Yeah. So I was saying you can't use that syntactic salt for anything other than the first memory location unless you either have +3 or you put the ampersand and the index.
Right. Yep.
Yes. Okay.
Yep. That's fair. Okay. So that's actually your first bit of pointer arithmetic. So I can set this to, name +2, because name is actually a pointer on its own. And then if I clear the output and I print this out, what do I see?
Oh, okay. Yeah, that makes sense then. Because it's going to keep reading.
Yeah, it's going to say name is really just the first location in memory. It's a pointer on its own. So I can actually look at name directly if I want to and say, like, what is name? Like, well, it's...
And it's going to be,
we're on a 64-bit machine, so I'm not using the right format specifier. But moral of the story is it's a big number. So, okay. So that does make sense, right?
Yes.
Okay, good. Sorry, I've been sort of missing what's going on, chat, but...
No, lots of help. Like, lots of people explaining things in different ways and giving examples, and it's helpful. So,
cool.
Chat is awesome.
Great. Now we can get to... That was the easy part. I'm sorry. So, now, earlier on, we were dealing with some examples where we always knew the size of whatever we were doing. And you were starting to say, like, well, what happens if we don't know the size and we need to dynamically say that it could be this big or it could be that big? Get more of the Python kind of like, I don't know how big it is, just, give me enough memory to do it.
Yeah.
Well, how do we do that? Well, we have to work with pointers, right? Because first thing we need to know is we need a place in memory to work with, right? And that place is probably going to move around. So I need a way to refer to that piece of memory. And that's typically done as a pointer or a pointer to a pointer, which is classically called a handle. But anyway, so let's do that. And I'm going to remove the struct stuff because we're not going to need it for now. But good job on that, by the way. All right, so there's two operators that we're going to see, and I'm actually just going to quickly throw this on the whiteboard because you're going to need to know both of them.
Okey-doke.
The first is, how do we get a chunk of memory dynamically? Well, your basic operator for this in C is malloc. And that's a memory version of the alloc routine. Alloc used to be implemented as a much lower level primitive that we're not going to be using in here. I don't want to see that kind of stuff in here, miss. So we're not doing that. But malloc was a memory allocation based on a particular size. And so it takes one argument, which is how much. And you tell it how much you want, and it always comes back because there's an infinite amount of memory and there's never any problems getting it. And you assign it to a pointer thing. And if you don't know what it is, you could even use a void pointer if you're being really naughty, but we're not going to do that. So we're going to assume that like we want to do a string. And I want, in the earlier example of name, let's say we don't know the size of the name. Then what we could do is we could do something like this. We could say name, which is a pointer, is going to get a nice chunk of memory, and we're going to specify how much we want. But the nice thing is we could change this later, and there's actually a call that's related to that, which is called realloc. And we can also, there's a few variants of this, but I'm really only going to cover malloc in here. All right, So malloc basically is give me a chunk of memory this big, right?
I mean, don't we still get back to the problem of like you need to know how much you need in the first place?
Well, that's always the problem. I mean, it's just that now you
Right?
have a way of allocating new memory, which you didn't have before.
Okay. I mean, is that not what we're doing when we say like care, 1000 or
But that's
something?
at compile time. Right.
Okay.
What happens at runtime? Like, let's say that we're pulling in some JSON and we don't know how much it is. Well, we can pull in like, a meg
I
of
don't
it.
really work a lot with compiling, so sometimes I think that distinction's a little fuzzy for me.
Okay. We'll get to that. Basically, in
Okay.
Python, compile time and runtime are sort of the same thing. So it's an interpreted
Yeah,
language.
so it's
In C, once you've compiled your program, that's it. You can't change it. So if you specified that a name is 20 bytes, that's it. It'll only ever have 20 bytes of memory. If you want to dynamically size that, then you're going to need this malloc call. And that's how you're going to say, like, give me 20 bytes. Okay, you know what? Give me 20 more. You know what? Give me 20 more after that. And that's how you can start dealing with like memory dynamically. The matching call to this is free. And this needs to refer to the pointer. And this is how you tell the system, okay, I'm done with it. So malloc, this is how you get it. Free, this is how you get rid of it. And everything will be fine, right? And this is where all the pain always shows up that you're reading about on Twitter, by the way, because you can free after there's all sorts of free errors because you might have forgotten to free something, your memory leaking. You might have double freed something because you freed something that you had accidentally already freed or another caller had freed and you didn't realize it. Like, this is kind of where things get a little crazy, is ownership. Who owns this memory? Who's responsible for allocating it and who's responsible for deallocating it? And that's where pointers start to get hard.
okay. That makes sense.
Okay, so armed with this information, let's do it. Let's set ourselves up with a name. So go ahead and give me name. This time, dynamically allocate a chunk, 5 characters. Well, all right, I'll give you 10 characters. Hey, what's up? Chats it up.
5 characters, like, meaning 40 bits?
Oh, this is bytes. This takes bytes as a...
Or sorry, yeah. Okay, so...
So you could just say 5.
Yeah, all right. Oopsies. Okay.
All right, so if we print out name, what do we expect to see? What is name itself?
It's a memory location.
Yes, it's a pointer. Right. So,
Right.
Which is a memory location. So if I printed it out, C would just tell me, okay, this is where you landed in memory.
Yeah.
Now, there's an important distinction with malloc. Malloc does not... So far, we've mainly been dealing with stack memory, which is, I explained before, with the winding and the unwinding. So that's where, like, this particular function gets this much memory and that's it.
Right.
Malloc breaks that rule. Malloc comes from heap memory, which is sort of this other pool.
Why?
Yeah.
Okay.
And it's typically managed using something called sbreak, which we're not going to get into, but it's a little bit. I don't want to go too far on it, like right off the bat, but basically it comes from a different segment of memory that we briefly covered in the other class. So let's stay more on practical. We'll get more to theory in the future. All right. So how do I put something into name? I mean, how do we put your name in there? Give yourself 10 bytes so that we have plenty of room. Malloc is an old Marvel villain. I like that, Strophium.
I'm actually... So is this like a buffer, kind of? Like
Yeah,
the
it is a
buffer that
buffer.
we were using previously? So we have to use like string copy?
Yeah,
Or...
that's exactly
Okay.
it. String copy would be the easy way to do it. The harder
What's
way
the
to do it
hard
would be like 1 byte at a time. You could put J in the first address and E in the second address. If you don't want to do that,
Oh.
I don't recommend it. Use string copy.
Okay. So let me remember. Oh, shoot. I remember like the syntax with the copy ones threw
Yeah.
me last time.
Yep, it always does. Gets me too.
So I was trying to find my notes on it.
Low bone lived in the heap.
Oh goodness. Let's see. Let's look at my. I think it was the week before that. Let me look at this. String compare. So we went over that. Here we go. String copy.
Yep.
Okay. So. Oh wait, hold on.
Oh, you need a new include for that.
Oh, okay. Oh, my bad. Sorry.
Oh, sorry. You should do it. What am I doing? Yeah, Malloc comes from the standard library.
Gotcha. Okay.
Okay, and what did you not do?
Oh no.
You dynamically allocated your memory. You copied Jesse into it. You printed it out, and you returned 0. First time ever, you dynamically allocated memory. You leaked it. So your program has a memory leak. Congratulations, you're now part of the club. Now you can leak memory with the best of us. No, it's not for shame. You're cool. Now you've actually leaked memory. You can't leak memory really in these other languages. Like JavaScript, it's still known by the interpreter. You're like, you don't really leak it. You just leaked it. That on an old operating system, that just sort of disappeared from the heap forever. So congratulations, chat. Let's give her an applause. Come on, I'm gonna give you like a real applause. I think chat should give you an applause. You did it. That is your first dynamic allocation. You have leaked memory and you've now properly corrected it, and I feel good about it. We're gonna get into advanced memory topics later because we're gonna be kind of shorter, and I think we need to have a quick scotch if we.
That sounds good.
Okay.